All right, so today we're gonna do an exam revision on engineering mathematics. So as far as I'm concerned, you guys told me to start with first order ordinary differential equations applications. So I take that we all understand the techniques on how to integrate. Remember, at the beginning, we started with the techniques on how to integrate. We have learned body direct integration. We have learned body separable, variable separable integration. We have learned linear integration. We have learned the Bernoulli. We have learned the homogeneous, right? So when it comes to the applications, we're actually going to apply all of those techniques that we have actually just learned. But when it comes to applications, you should be able to see which technique are you going to apply when you solve a given equation or a given problem. You understand? So here it's all about those applications. It's all about those techniques. So now, without wasting time, let us just start with the session. So now, when we start with the applications of first order differential equations, we are looking at these are the applications, by the way. The first application, we're going to look at the population growth or the exponential growth. I've already did a video on this application, but I will do one question from semester test. There was a semester test that was written 2023. They did this question, so I took one of those questions from semester one, first semester test, which was semester one from 2023. I will do one question from there, but I can also send you guys a link of my YouTube channel where I did one of the example of population growth. And therefore, the second application that we're going to look at is a radioactive decay, which can also be called the exponential decay, right? So this is one of the applications of the techniques that we actually have learned at the beginning of the year. And then the third application is Newton's law of cooling. Newtonian's law of cooling. Um, it's one again of the applications. If you are in chemical, you might be familiar with this. And therefore, another application, it's mixing problems. And the reason why I highlighted this, I don't know if you guys have already got the scope or whatever from your perspective lectures, but it's fine. Nonetheless, in a nutshell, mixing problems, let's be fair, we've been doing mixing problems since from I think semester test one. Even on our class test, we've been doing mixing problems. So honestly speaking, we can't expect mixing problems to come again, right? Because now we are heading to the exam. We can repeat one thing over and over and over again. What about the other applications? Why do we always keep on doing mixing problems? So mixing problems for today, in a nutshell, let's just not do it. You understand? I don't know why, but it's just the logic. We've been doing these questions over and over and over again. Um, Make sure that you attend your lecturers, guys, for scopes. Okay, probably they will give you details here and there. Now, I'm not saying it's not going to be there. I'm just using the logic because we've been doing mixing problems, so I'm not going to do it for today. We'll do it next year. And therefore, we have the electrical circuits. That's where we're going to talk about body RC, body LC, LR, RC, and all of those things. We also going to look at those problems. But for this one, for now, electrical circuit, I'm not going to do it because it needs its own time. So yeah, I don't want to make this session to be long for no reason. I know, like focus. But again, the span of focus, guys, it's short. So we can't do electrical circuits for now, right? So now what I want to do is I want to discuss the standard forms of all of these applications. Okay, remember this will be up 3, 4, and 5. So far we have 5 applications. So then growth. What is the standard form of that? So that's what I want us to do. Okay. So now when you talk about the population growth, like we see there, it's our number one. It is more or less like you need to know the equations, because remember in exam, what they're gonna do is they're gonna give you a scenario or a problem. you have to figure it all out. Which application am I going to apply? Which equation am I actually going to work with? So meaning these standard forms, they will actually help you to understand how to go about for a certain problem. So for population growth, okay, a standard form for population growth is more like a formula. It's given by D and divide. Sometimes it could be dp, p representing population, you understand. dn over dt is equals to k multiplied by n. You can represent your population growth standard form just like so. Okay, like I say, don't get twisted in future when you get something like this. dp over dt is equals to k multiplied by p. It is still the same thing. It is just that our p here is it's denoted by p. Population is denoted by p, and then here population is denoted by n, which is number of population. N, number of population. P, population. You understand? So it does not matter how you represent your population growth. And number two, remember we spoke about what? We spoke about the radioactive decay. So radioactive decay, it is also denoted, the standard form, it is also kind of the same of the population growth. So here we'll be looking at dA divide by what? Divide by dt is equals to k multiplied by a. This is again the standard form of our radioactive decay or our exponential decay. Okay, there's a standard form. You need to know them, guys. It's very important because they will help you to solve the problems moving forward. And then number three, we're talking about the Newtonian's law of cooling. And what is the standard form of this one over here? The standard form for this one, it is given by dt divide by dt is equals to k into t minus t sub m. So this, it's the equation or the differential standard form equation for what we call the Newtonian's law of cooling. Okay, so guys know these standard forms. And then we'll discuss what does T mean. T simply talks about the temperature, okay, at this point in time. And then this T here, the small letter T over here, it represents time. Okay, and then K, it is just a constant based off this equation or based off this formula that we see over here. And then T sub N, it is the temperature of the surroundings. Okay, for an example, I will be telling you that my phone, it generates temperature itself, right? But now the temperature surrounding my phone, it is 123. So Tm, it is the temperature surrounding my phone, of which my phone generated. Maybe my phone is generating a temperature of 60 degrees. I'm just making an example. And then this temperature surrounding, it's 38 degrees. You understand? So that's the difference between this T and that T. But we'll look at that when we solve a question, right? So that it makes sense to us. So, and then for number four, we have the mixing problem. Like I said, we'll do it next year if we're going to have to repeat our maths. And then for number five, we're going to look at the electrical circuits. And then this one, the standard forms, I'll do them later, if not tomorrow or whatsoever, because like I said, this one needs its own focus because it has a lot of things involved, okay? And I want you to understand how the standard forms of electrical circuits actually goes by. So now we're going to focus only on these three parts where we're going to look at the population growth, standard form, radioactive decay, standard form, Newtonian's law of cooling, and this is the standard form, right? So please, guys, make sure that you familiarize yourself with these standard forms moving forward. I'm sorry about that, guys. Let me just. Sorry about that. Sorry about that. I apologize about that, guys. All right. So yeah, so these are the standard forms, okay? So let's make sure that we familiarize ourselves with this. Now, let us go through the questions. Remember, we are doing the application. So when we are doing the application, we expect to be given a scenario. So with this scenario, we're going to learn on how to apply those techniques. Remember, the techniques are very important. So what I've realized is all of these questions, if you pay attention, the most, the application that we normally use, the technique that we normally use under the applications, we normally use the variable separable, if you still do remember variable separable. So meaning if this side you have dt, maybe this side of the equation you're supposed to have dx, and then you can integrate it like this. You have to separate your derivatives first before you can integrate. But nonetheless, let us just start with by solving this problem. Now they say to us, the table below displays the exponential growth. You see, okay, now they're telling us, wait, what is it all about? Exponential growth of the population, right? So now, something is hiding my view. I don't know why. See, okay, let me move this thing over here because I cannot see what's written. All right, so it says that the table below displays the population growth of the population. So here, population, it is noted by a letter P. P is equals to P at T of a country in a specific year. Oh, okay. We're talking about the population growth here over years. We can see that we have year 1992, 1997, 2007. And then what's happening with the population? By just looking at these two numbers over here, we can see that the population is increasing. The population in 1992, it was 827. And in 1997, it was 949. We can see that the population is growing. That's logic, right? We know that population grows year by year. And then now, they say to us 2.1 for 8 marks. This from semester test 1, I think. They say determine an explicit expression for P at PT, the population with respect to time. So what's happening here? What do we want to do? We want to determine the explicit expression. And here's the thing. There is a difference between guys, we should be able to know how to answer these questions. They say explicit. There is implicit and there is explicit. When they say explicit, so that means you need to determine your equation in some sort of a simplified form. I will tell you when I get to the final answers, close to the final answers, I will show you the difference between the explicit expression and the implicit expression before I can get to the final answer. Before I will get to my final answer, I will have my implicit. And then when I go to my final answer, I will have the explicit expression. You understand? Okay. Just want to be practical on this one because we'll be trying to explain and it wouldn't make sense maybe. So we'll do it practically so that we can see what does that mean. So now to solve question number 2.1, what do we want? We want to determine the equation. We want to determine the general equation or the particular equation. That's the question. Remember, what we're going to do, we're going to formulate ordinary differential equation, first order differential equation. That's what we're going to do. And then after forming that first order differential equation, we're going to integrate that equation. After integrating that equation, we're going to get the solution. And the solution that we're going to get, it is called the general solution because the solution has constants. But because we are given the conditions over here, we're going to take these conditions and then we're going to plug them onto our general solution. After plugging these conditions into the general solutions, we're going to get our constants. And then after getting those constants, we go back to the general solution, we substitute the constants, and then now we'll get the particular solution. So basically, this table over here, it shows the conditions. Okay, so these are the conditions provided. Aha, so now remember I told you it's important for you to know the standard forms. So here we are talking about the exponential growth and of the population. So what is the standard form? The standard form, it is D. Okay, here we are using capital letter P instead of N. We're going to say P divide by dt is equals to K multiplied by population. They didn't tell you use this equation. You should be able to know it by yourselves. Okay, so this is the equation that we're actually going to use. Let me erase there. Fix my 18 there. Right. So now after here, what now are we going to do? We are going to integrate. Can we integrate the equation that looks like this? No, we cannot. Why? Because we cannot do the direct integration. We have dp, we have dt one side. So which type or which technique of integration are we going to use? We can use separable. We can cross multiply. So when I cross multiply this, here I'm going to have dp, and then this side I'm going to have k p dt. I just cross multiplied. Remember, this is the same as over 1. I just cross multiplied. And therefore, you see I have p variable over here. I want to get rid of it. I want to take it this side. So I'm going to have to divide. So I'm going to have 1 over p multiplied by what? By dp, which is equals to k multiplied by dt. I don't care about k because k, it is just a constant. So now, would I be able to integrate this? Now we are talking about the integration techniques, the one that we started with at the beginning of the year. So what type of integration is this? It is variable separable. We had to separate our variables, right? So now let us integrate. So when we want to integrate this equation over here, we use the definite integrals, not indefinite. We use indefinite, not definite, because we don't have the bounds. So now what we're going to do over here is, what is the integral of 1 over p? Don't be a superhero. If you forgot, this is the final exam, they're going to give you the formulas, right? If you forgot on how to integrate, always refer to your formula sheet. So the integral of 1 over p, we know that it is given by ln, or natural log of p. Right? You don't have to write c. I understand. This is the definite integral, right? This is, sorry, indefinite integral. You don't have to write c. We'll write c only this side. Do not forget that. So now, what is the integral? Oh, by the way, let me just do it like this. This is a constant. If you still do remember, I'll just log it outside. Just keep it there. It's a constant, right? So I'm Hello, guys. Hello.
Yeah.
Um, I think it's my network, but it's fine. It was okay. It was a router issue, so let me try to reconnect again. I'm sorry about that. Is everything fine though? When did I start to break?
From integrating.
Okay. Um. Okay. Let me do this. Okay. All right. Am I audible? Please confirm before I continue. Okay. Thank you. I see the thumbs up.
Yes.
Okay. Thank you. All right. So I was here. Did we manage to see this part?
Yeah.
Okay. So yeah. So I was saying this is this thing over here, dp dt is equals to kp. This, it is the first order differential equation, right? Okay, let me just say it's the differential equation. And then this thing over here, it is our general solution. You understand? This is what you did as a technique, right? But we are given the conditions. So how are we going to use these conditions to determine the particular or the specific solution? By the way, you can just add your equation over here. Oh, this is what I said. I said I will explain the difference between the explicit and implicit. You see this equation over here, it is implicitly expressed. But when I want to solve P, when I want to make P subject of the formula, I'm going to have to introduce e to the power of ln P. In this side, I'm going to have to introduce e as well. You understand? That's implicitly. But if I want to express this general solution explicitly, then I have to make P the subject of the formula, and then that will be my answer. Basically, there are two answers. There are two ways how I can present my general solution. Now, right now, it is implicitly expressed. Okay? Right. So this general solution. Now let's talk about the conditions so that we can plug them over here. Why? So that we can get our constants, which is K and C. But firstly, let's see how does the conditions stand by. They said at the year 1992, we'll take year 1992 as our reference. So we'll take it as year zero, initial year. You understand? So meaning 1992, it is our initial year. And then at 1992, we had this population over here. So meaning we remember this is the same as I guess is the like I said, if you want to solve P explicitly, you're gonna have P is equals to blah 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 blah. At the end, you can express your P like this: P at T is equals to blah 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 blah, to show that this is the general solution to this equation over here. You understand? So meaning meaning our P initial, which is T inside. Remember, T, it's time. So, or we'll represent in terms of years because here we have years. So, meaning in this case, our T in this years, it was 0 because it was initial. Do you understand? Is equals to what? When time was 0, our population was how much? It was 8. It was 8. It was 8 to 7 initially, right? And then we can start by using this condition first, okay? And then after we'll move to the second condition. Let's start by using this condition first. So using this condition, what are we going to do? We're going to substitute it into the equation. So ln at the P, inside of the P, it is our population. So that means we have ln of what? Our population is 8 to 7 is equals to K, which is our constant. Our time, it is 0. So hence why here T, we substitute 0 because that's initial, plus C, which is our constant. So we can see that this will fall off, and therefore the value of C will actually be equals to ln of 8 to 7. So we managed to solve the first constant, which is C. So now let us rewrite this equation. Now substitute in C. So meaning we're going to have ln of P is equals to K multiplied by T. And then what is the value of C? It is positive ln of 8 to 7, and then the bar. Right? So now we need to solve for value of K. We're going to use the second condition. The second condition says in 1997, our population was 949. And remember, I said here it means years, which is time at this point in time. You understand? So from 1992 to 1997 is how many years? We reference, remember, this is 0 From here to here, it's going to be how much? 1992 to 1997, you can just say 7 minus 2 will give you 5. So meaning from 1992 to 1997, that's 5 years. Meaning at a year 5, what was our population? It was 949. You get it? Again, we go back to this equation. Now we want to solve for k. We're going to substitute 949 where we see p. So that means here we have 949 is equals to k, and then our t, it is 5 plus ln of 8 to 7. Right? Now we can solve for k because these are just numbers. So to solve for k, I'm going to say my k from this equation will be equals to, I have ln of, okay, should I do it step by step now? You guys, by now, you should know how these things work. 4, 9. Remember, when we minus, we divide. I get then the rules of this. We have 8, 2, 7 there, divide by 5. So this will be our value of k. So let's solve it maybe to 2 decimal places. You can also help me by punching this on your calculator and tell me how much you get. Please confirm if this is correct. On my calculator, I get 0.027 to 3 decimal places, 5, 2. Okay, let's just leave it here. So this will be our value of k, which is our constant. We go back again to this equation, which is the general solution. We're going to plug all of the constants. Then our equation will look like this. So we have ln p is equals to, our k, we said it's 0. Remember here it's k, right? Yeah, here it is k. Our k, we said it's 0.0275 multiplied by t. Oh, it's happening now. Okay. Okay. Here we have t. We go back here. There we have t. And then ln this plus ln of 8. Confirm 8 what? 27. 27. And therefore, this is the answer. So basically, this is the final answer. Ne? But they did not say determine your expression implicitly. They said explicitly. So you can't leave your answer here. Unless if they said implicitly, or unless if they never said anything, you can leave it here. But because they say now explicitly, now we're going to have to solve for p. So how are you going to solve for p? We're going to introduce what? We're going to introduce e on both sides, exponent on both sides. We're going to introduce e to the power of, remember when we do this, ln of p is equals to, even this side, we're going to do the same thing. E to the power of 0.0275 t plus ln of 827, this. So this side, ln of e to the power of ln of p is going to give us p, if you still do remember. And therefore here, we are adding the exponents, laws of exponents, same basis. When you multiply the same basis, you add their exponents. So e is the base. So we have addition, we separate, that means we are multiplying. So this is the same as e to the power of ln 827 multiplied by e to the power of 0.0275 t. And therefore p will be equals to how much? Ln or e to the power of ln of this 27, we're going to have 827 multiplied by e to the power of 0.0275 t. Therefore, this will be your final answer explicitly. This will be your final answer implicitly. That's the difference between explicit answer and an implicit answer. Or you can even write it like this, P at t, because remember, this is your variable. This is like exponential graph. Y is equals to a, b, x. So x in this case, it is t, and then y in this case is going to be p, and therefore base, which is this, is going to be e, and then a in this case is going to be this number over here. So basically here, we just managed to determine the solution to that differential equation. So that means you can also express your answer just like so. And therefore, this will be the final answer. You can write it like this or like that. It really does not matter. That will be 2.1. So guys, do we have the questions regarding this? Am I being fast? Am I not being clear? What's the deal? You want clarity? Talk to me. Please, guys, talk to me. We are fine. We understand. Yes, yes, LM.
Just give mistake. I was reacting. I wanted to react.
Okay, you understand.
Yeah.
Okay, Giddy. Lituli. Lituli. You understand. Okay, I'll take that you guys understand. Ehlongwana? I believe. All right. So now I'm gonna move to 2.2. I'll just write it here, okay? So now we're going to move to 2.2. Now 2.2, it says to us, calculate the population of the country in 2007. You see, we don't know what was the population over there. So we want to know the population. Again, this is the reference, and this will be then our final. So this will be initial, that will be our final. So meaning we want to understand from 1992 to 2007, how many years are we looking at? It's simple. Take your calculator, say 200. Say 2007, subtract 1992. Basically, you're going to get what? 2007 minus, it's how much? 15 years. That's like 15 years. You understand? So meaning we want to understand what will be the population of, what will be the number of population in 15 years starting from 1992. So to perform this calculation over here, we determine our general solution. So make sure that the general solution is correct, or else you won't get the correct answer. So meaning at this point in time, we want P at 15 years, which is our time. So that means we substitute T there. We have 827 multiplied by E to the power of 0.0275. And therefore our T over there, it will most definitely be 15. And therefore when we punch everything on our calculators, so we say 827 multiplied by the exponent of what? 0.0275 multiplied by 15 on my calculator. You can also confirm on my calculator, I get 1,249.26. But remember, here we are talking about the population. We can't have the number of people. How many number of people are attending civil engineering? There are 120.7. It doesn't make sense, right? So let's round it to the whole nearest degree. So meaning it's going to be 1,249. Roughly, we are talking about this population over here. And then that will be 2.2. Okay? So that's how we go about for these questions. Now here's another question of application. We're still going to repeat the same thing. What's important? Know the standard form, know how to get your conditions, apply those conditions, get your constants. That's it. So now, this question here, it says to us, a breeder reactor converts. This thing's gonna hide my view again. Let me move it here. Okay, good. So they say to us, a breeder reactor converts relatively stable uranium 238 into the isotope uranium 239. After 15 years, it is determined that 0.043% of initial amount of A initial, which is the isotope has disintegrated. Determine the half-life of this isotope if the rate of disintegration is proportional to the amount remaining at time t. Now, I said to you the application, it's population growth. We just did a question on population growth. The second application, it's radioactive decay. So this is the radioactive decay. This is the exponential decay. Okay. So when we talk about the decay, most definitely we're talking about the disintegration. So something when it decays, we say it disintegrates, right? Meaning it breaks up into smaller parts. You understand? So now what's happening over here is we are talking about the population degrees. Okay, so what is given and how are we going to use what is given? That's very important. Now, look, let's start first with the standard form. We'll do the rest after. Ne? We'll reanalyze the statement after. Here we are talking about the decay, and I told you that when you talk about the decay, the standard form, it will be, you see, it's exam. They are not telling you what to use or what to do. So this is dA over dt, which will be equals to k multiplied by a, right? This is standard form. And then from this standard form, what do? This is like 3 marks. You integrate, right? Separable again. So I'm not going to tell you that. You have to know it. So by just cross multiplying, this side I'm going to have 1 over a dA. I'm jumping some steps from what I did on the first question. Is the same thing, by the way. You can do it like that if maybe you're confused. And then here we're going to have k multiplied by dt. My aim is to make sure that I have dA this side, I have dt this side. Everything that says a this side. And then constant, it could be this side, could be that side. It does not matter. And then from which is k, I'm referring to k. And therefore from here, what we're gonna do, we're gonna integrate. You see, we are repeating the same thing now. We're gonna have to integrate. It's gonna be inside because this is not the constant. But k, I'm gonna log it outside because the constant, right? And therefore now let us integrate. Now integrating this side was the integral of 1 over a in respect to a. So means we're gonna have ln of a is equals to, what is the integral of dt? 1 dt is going to be kt and plus c. Why do we add c? Because we are talking about the indefinite integral. We don't have the bounds here and there, right? Sharp. So that's it. Now from here, we have the general solution. From this general solution, we need the conditions. Let's go again from our statement so that we can understand what's happening. So the statement that is very important over here is this one. This is the most important statement over here. Okay. Apparently, we have the initial isotope. So the initial isotope in this case is going to be what? The initial amount. This is indicated. It's A naught, A sub naught, right? We don't know how much is it. They just said, we don't know whether it's 16, it's 20, is what. They just said the initial amount is A sub naught. So at the initial, we know that the time at initial will always be 0. So that means the first condition over here, we can see that we have A at 0, right? This is the time, which is 0 initial. And therefore initial, what is the initial amount of isotope? It's A sub naught. We don't know what is it. It's just A sub naught. Initial amount of A sub naught. You understand? And therefore, okay, we'll come again to read this. I just want to give you the technique on how to solve these questions. And therefore, now let us substitute this condition over here. Now, to substitute this condition over here, here we're going to have A. A means our isotope. So our isotope is A sub naught. It's initial. We don't know how much is it. So we'll just substitute it as it is. Here's going to be A sub naught, which will be equals to K. And then our time most definitely is going to be 0 plus C. And therefore this is going to fall out. Therefore we can see that our value of C is going to be ln of A sub naught. Close this. Now we go back here. We're going to substitute the value of C. Now we have what? Ln of, let me see, A, which will be equals to KT, and then C, we said it is plus ln of A sub naught. This is the equation. But we're still running short of k. We need to solve k. But the question is, how are we then going to solve for k? We need another condition, right? This is the initial condition. Already utilized. Thank you. Let's go to the statement. They said after 15 years, for the fact that you see 15 years, here again, time, it is in terms of years. You understand? So number one, you can see over here we have A at 15. You don't have to panic. Or you don't have to stress yourself. Take it as if you're a mathematician. You are not a radiologist or whatever. So A at 15 is equals to what? They said at 15 years, it is determined that we had 0.043% of initial amount of our isotope. Do you understand? And then again, it's important to read the statement fully, guys, because you might even get this one wrong. Let me help you out because you're going to be confused. Okay, why am I not multiplying by 0.043? Okay, here's the thing. They said after 15 years, like it is determined that we had this 0.043% of the initial amount of A sub naught has disintegrated. When they say has disintegrated, meaning 0.043, it has broken down, meaning 15 years later, the remaining part. Okay, let me make it make sense to you. Ne? Listen to this. Let's say we have our initial was 100. I just want to make sense to you so that you can understand. Let's say our A sub node was 100. Ne? Just making an example. And then they say to us, 15 years later, we had 20% of this. This would make sense. 15 years later, we had 20% of 100. Remember, we multiply when you say of 100. Right? We multiply when you say 100. So I know, guys, you would be tempted to do this. I know you would be tempted to do this. And then the answer that you're going to get over here is going to be how much? It's going to be 80. So I'm going to multiply by 100. It's going to be, sorry, it's going to be 20. You're going to get 20. And it's going to be wrong. The answer that you're going to get over here is supposed to be 80. Here's why. When they say disintegrated, they say 15 years later, 20% of 100, it has broken down. So that means if 20% is broken down, meaning this 20, it is no longer there. It doesn't exist 15 years. That means we are left with what? If 20 is not there, therefore that means we are left with 80. After 15 years, it is determined that, let's use 20%. 20% of the 100 has disintegrated, meaning 20% of 100, it is dead. It is no longer there in 15 years. Meaning, okay, if 20% is not there, what is it then? It is 80%. So that means to go about for this calculation, be careful, guys, and learn how to read because that's very important. So that means we're supposed to say, we can say 80% minus, we can say 20% minus, we can say 0.2 minus 1. So even here, that's what we're actually gonna do, okay? I hope that was clear, guys, please. If it is not clear, let me know. So meaning here, I'm gonna say this 0.043% is gonna be the same as, remember 0.03%, I can say it's gonna be the same as, I can use 100%, however you wanna do it. Look, however you wanna do it. I will do it like this. 0.0, I don't know why am I punching this on my calculator, but I don't wanna make mistakes. So this is going to be the same as what? 0.00043 when we convert this percentage into decimal, right? When you convert this percentage into decimal, right, which is 0.043. So I'm just going to punch 1, subtract 0.000, ne? 43 multiplied by A sub naught. And therefore, this will give me how much? Let me see, minus 1. It will give me 0.99957 times A. I hope that logic that I did over there, it managed to help you. So this is the another condition instead of this condition. Now we have the second condition over here. Right, so now let us go substitute. So here we're gonna have ln of our A in this case is gonna be how much? It's gonna be 0.99957 A sub naught. The bar this side is equals to our K, is what we are looking for, and then our T, it's gonna be 15, and then plus, there we have our C, which is ln of A sub naught. This one I'll do it step by step so that we don't get confused. So now here what I'm gonna do is, now I'm gonna say here I have ln of 0.99957 A sub naught, close this, subtract, I'm taking this one this side of the equation, so it's going to be negative ln of A sub naught is equals to 15 multiplied by K. Remember, when we subtract the laws of logarithms, when we subtract the ln, we do what? We divide them, right? So meaning we're going to have ln of 0.99957 A sub naught divide by A sub naught, close this, is equals to 15K. So this and this will fall off, and therefore I'm going to have ln of 0.99957 divide by 15. This will give me the value of K. I have C, I have K, I can substitute them here, and then I get my particular solution. So now let us go and substitute. We have ln A, so we're gonna have ln A is equals to K. Our K we said is how much? I don't like writing the fat, but let's round it to two decimal places. So we're gonna have ln of function, ln of 0.99957 divide by what? By 15, so that we can get K. Yo, no, I'm not gonna round. I'm not gonna. It gives me 0.0000 something. I don't like it like that. I don't even want to express it scientifically. I'll just write my K as it is there. So our K, remember, I'm here. I'm substituting K. Okay, so this is my K. Don't forget. It is ln of 0.9997 what? 57. 57. So 57 divide by 15. This is K multiplied by T. And then what is our C? We said our C, it is ln of what? What is C? Oh, there. It's plus ln of A sub naught. So now what we see over here, ne? This is the final. Okay, this is not the final answer. This is the general solution. Implicitly. This is the general solution implicitly. Ne? So now what we're going to do is they didn't tell us whether to determine this. They want us to determine the half-life. So we need to determine the half-life of this isotope. So when we talk about the half-life, what are we talking about? Half-life of the isotope, meaning we multiply isotope by half. So we need to determine the half-life of this isotope. Rate disintegration is proportional to the amount of remaining. So meaning basically we are looking for number of years or for time. So meaning ln at, we don't know what is the time over here. I'll just put the question mark, which will be equals to half-life of our isotope over there. So that means we want to determine the half-life of the isotope. So now, then how are we going to go about for this one? Sorry, guys. So because there we have our answer already, ne? You don't have to remember, you don't have to perform this step again. take this one this side, and so that they can cancel over here. You can just literally write half. Okay, you don't have to resubstitute because automatically it will do the same thing. You can just write half over here is equals to, here we have ln of 0.99957 divide by 15 multiply by t, which is what we are looking for. Yeah, it's gonna be like this. Like I said, you don't necessarily have to substitute half. You can do it, it's fine. If you maybe think you're gonna make mistakes, you can substitute half over this, and then we take this one that side again, and then we're gonna end up with something that looks like this. You understand? So now our t in this case will be equals to how much? It will be ln of 1 over 2 multiply by 15 divide by ln of 0.99957. I don't like to round. I would rather round off my final answer. So please also confirm with me using your calculator. So here I'm going to have ln of 2 multiply by 15 divide by ln of 0.957. And then the answer that I get is 4,174.35, blah, blah, blah. Again, so here, because we are looking for years, we can round it to the whole nearest degree. Okay, so we can conclude by saying the half-life of the isotope is approximately 24,174. And this will be our final answer. I am patiently waiting to see if you guys understand or not. Do we all understand? Do we have question?
Can I ask?
No problem. Yes.
Moiki, I think you lost me on. You said the part you learned 1/2.
Okay.
I don't know. Are we not supposed to use 1/2 or something? Or
Okay.
already you calculated?
It is, you're confused here, ne? Right?
Yeah.
Okay. It's fine. Look, do what you feel comfortable with. It does not matter, ne? You are writing your final exam. Do not forget that. We want to say goodbye to mathematics. So what I did over here, ne? I have this equation over here. And then this is like, I'm looking for time. It's okay. You can just remember our ln A, which is isotope over there. We're going to have ln of 1 over 2a this, which will be equals to, you can substitute the equation there, which is ln of 0.999 what 57, right? Divide by 15, multiply by time, and then we have ln A there, sub naught. So remember I said, if you take this, let's take this one this side, it's going to be negative. It's okay, you can do it like this. It's okay, it's not a problem, it's not a train smash. Divide by 15, oh, multiply by t there. Here I think it's plus, and then I'm supposed to multiply by t there. Just made a mistake there. Ne? You see it? Are you following? Okay. The thing is here, when you subtract, remember the laws of logs, the laws of ln, those laws. So when you subtract, you divide. So eventually, you're going to have 1 over 2a this divide by this one, which is a that, which will give you this side, which is ln 0.99957 over 15 multiplied by t. So this will cancel this, and then now it will take you to this step.
Okay, I see it.
So the thing is, okay, let me explain how I got here. The thing is, remember we did some sort of an example like this. Ne? So that's why you will see body memorandums, they just jump things because they assume that you will understand. We did the same thing over here. And I told you that if this number over here, if Wamaki is sub not, so you don't have to start again and perform all of these things. You can just simply come here and substitute this number over here, which is 1 over 2, instead of you substituting there, taking this one this side, you understand?
Yeah.
Yes, but it's fine. You can do it like this if because it's your final exam. Do what you are comfortable with. Try to push as much as you can. Is that fine? All right. See the thumbs up there. Now, remember the applications. So far, we did the population growth. I'm reminding you. We did. That's how you study, right? You remind yourself what you did so that you don't get lost. You did the population growth. We did the radioactive decay, which is the question that we did. And then now we're going to do this question. Let's see if this question, they're not going to tell you by the way in exam. You have to figure it all out by yourself. Now they say to us a thermometer reading of 40 degrees Celsius is brought into an air-conditioned room at 20 degrees Celsius. After 2 minutes, the reading is 35 degrees Celsius. Okay, I see you. I see you what you did there. So now, which application is this? Most definitely is going to be Newtonian's law of cooling. So Newtonian laws of cooling and Newtonian's law of cooling, remember the standard form. It is different from the population one. It is different from the radioactive one. The radioactive and population, they have the same, just that you will change the the letters. There it's P or N, there it's A. So here, Bona, look, my chair is bending. Let me fix it. Look, um, what did I want to say? Before you can even solve, you can just figure out what's happening, write a standard form without even you reading. Just check. Oh, I can see. We are mathematicians, guys. We just want to solve the answers. We don't want to understand for now, right? So what we do is you write the standard form. We saw already this is Newton. So it's D. Remember, for Newton, we use the temperature and time, right? If you still do remember. So it's gonna be dt divided by T, this is time, this is temperature, is equals to, constant will always be there, K, multiplied by T minus Tm. So this M, it means medium, okay? Or you can say Ts. S means surrounding. It is still fine. You can substitute with S there to show its temperature of the surroundings. I mean, like, this is you, right? You have your own temperature. Your own temperature, let's assume, is 35 degrees Celsius. But the temperature surrounding you, it is not the same as your temperature, unless if you have to reach Boma equilibrium. So that means this temperature, T, it's your temperature. But this Tm over here is the temperature of the surrounding. You get my point? So now that means a thermometer reading is 40 degrees Celsius. So meaning this will be the temperature of the thermometer. Is brought into an air-conditioned room. So the air-conditioned room, the room has surrounding. The room is the surrounding, right, of the thermometer. So I mean the temperature of the surrounding is going to be 20 degrees Celsius. You get it? So after 2 minutes, the reading is 35 degrees Celsius. Meaning after some 2 minutes, they're telling us the reading it is 35 degrees Celsius. Okay, you know what? I don't like talking about these things for now. We are coming. So let's just do the basic thing that we normally do. Let's do what we are good at. So here's the standard form. From this standard form, what are we now going to do? Apply the technique of integration. Again, this equation is now it looks similar, it looks different from what we did. Ne? Are we still gonna apply? Are we gonna now apply Bernoulli? Are we gonna apply linear? Are we gonna apply separable? Are we gonna apply homogeneous? We're still gonna apply separable to make our lives easier. Ne? So what I'm gonna do is, remember this is the same as over 1. I'm gonna cross multiply. When I cross multiply, I'm gonna say this multiply by that. I'm gonna get my dt. is equals to this multiplied by that. I'm going to get k t minus t sub m multiplied by dt. Okay, t one side, small letter t other side. So I can see here capital letter 1. I'm going to divide everything by t minus tm. So here I'm going to have 1 minus t minus tm multiplied by dt, and then this side I'm going to left with sorry, this side I'm going to left with k multiplied by what? Multiplied by dt. Now I separated my variables. Capital letter t one side, small letter t one side, k wherever you are, I really do not care about you, right? So now let us integrate then. So this is separable, we can see. So we're gonna, this is not a constant, so I'm gonna log it inside. This is a constant, I'm gonna log it outside of the integral sign. And therefore, now what I'm going to do is, now what is the integral of this? It's the same as ln, right? Just that here we have t minus tm. So we're going to have ln of t minus tm. We don't need c, we'll just write it only on one side. We have k here, ln of 1 dt. We know by now it's t. We are bringing back t plus c. See, we are repeating the same thing over and over again. You cannot tell me that mathematics is hard. It's not. It is not. Right? So now this, it is our what? It is our general solution. This is our general solution. Remember, from this general solution, now what do we need? You can all agree with me. We need the conditions after this step. You should know it by now. So now we are given that a thermometer reading, obvious, is 40 degrees, is brought into an air conditioned room at this. Obvious, this is the initial temperature of the thermometer because it is just brought now, right? So meaning at this point in time, temperature initial, remember this time initial, which is 0. Oh, let me write it here. I'm used to writing it here, remember? Our initial temperature at this point in time is how much? It is 40 degrees Celsius. And therefore, Tm will always be the same. After 2 minutes, after 20 minutes, after what? Unless if they change it, Tm will always be the same, will always be 20 degrees. So our initial temperature is this, and then our Tm is also there, which will be 20 degrees, right, of the surrounding. Now let us substitute then. So here we're going to have ln of our t, it's 40 at initial condition, minus our tm is going to be 20, always will be 20, and then k, our t, that's going to be 0 time, it's 0 initially, plus c, we need to solve for c. So this is going to die off, and therefore we're going to have ln of 20. Ln of 20 this side, which will be our value of c. Right? Right. Now, what are we going to do? We go back to this equation, we substitute. So we have ln of what? T minus Tm, which will be equals to K multiplied by T, and then our C will be ln of 20. Now we need to solve for K. We need another condition. They said after 2 minutes. Another time, remember we started with initial time which was 0. So now they're telling us after 2 minutes, oh, t at 2 minutes, it's no longer initial, right? T at 2 minutes, after 2 minutes, the reading is how much? The reading is 35 degrees. So meaning we have 35 degrees Celsius over there. Right? So now let's go. Now we're gonna substitute. We have ln of, remember Tm will always be the same, which is how much? 20 degrees Celsius. So we have ln of our T is gonna be at 2 minutes, it's gonna be 35 degrees Celsius. Subtract Tm will always be 20 degrees Celsius there. And then we have K, and our T now it's 2, it's no longer 0, plus our C. C is already solved, which is ln of 20. And therefore, from here, we're going to say we have ln of what? It's 5. Right, no? Why my maths is not 15? 15. So here we're going to get 15, which will be equals to 2k, my 2k plus ln of 20. Then transfer this one this side. When I take ln of 20 there, if you still do remember, I'm going to have 15 divided by 20. is equals to 2K. So you can simplify that 15 divided by 20, right? Which is going to give us 3/4 or 0.75. So we're going to have ln of 0.75 divided by 2. This will be now the value of K. It's our constant now. I have already divided by 2, by the way. Okay. So let's go back here and determine that. Then we have the particular solution. So our particular solution will be ln of T minus Tm is equals to K. K, we said is how much? Is 1/2 ln 0.75. So we have K, which is 1/2 ln of 0.75 multiplied by T. And therefore, what is our C? I'm using this. Where is that thing? I'm using this. I know my K, I know my C. Therefore, my C will be how much? Where is it? Ln of 20. So meaning we have plus ln of 20. So this is the general solution. Sorry, the particular solution, because we have K and C. If we don't have K and C, that's a general. But if we know the C and K, that's a particular. Now from here, then what are we going to do? Let's answer this question. You see, you don't even have to read the questions before, but it's important, guys. Please read the questions before you answer. Here we just following the pattern. So now, how long take until the thermometer is practically at room temperature? Say room temperature is 20.1 degrees Celsius. How long it will take that? So meaning how long it will take the thermometer. By the way, you saw the thermometer initially it was 40 degrees. After 2 minutes it was 35 degrees. We can see that the temperature is decreasing. But how long will it take it to 20.1 degrees Celsius? From 40 degrees Celsius to 20 degrees Celsius, it took 2 minutes. Sorry, from 40 to 35. From 40 to 35, it took 2 minutes. So we want to know, until it gets to 20, how long is it going to take? It's simple. We just use this answer over here. Now we answer, we're still answering number 1, by the way. So we're going to have ln of, sorry about that. Our T is how much? T at the time that we're looking at is 20.1. Minus T of the surroundings, which is always 20. So the reason why they put 20.1 over here is because 20 plus 20 will give you ln 0, you understand? And I'm sorry about that. Oh, and we know that ln 0 is undefined. That's why they say 20.1 is equals to, I'm sorry about that, flu 1/2. Here we're gonna have what? Ln of 0.75, we are looking for T, plus ln of 20. So basically, you can just punch everything on your calculator. So what I'm going to do is, yeah, I'm sorry about that, guys. It's just my flu. Forgive me. So now what I'm going to do is, you can just do it like this. 20.1 minus 20 minus ln of 20, and then divide by what? Divide by 1/2 ln of 0.75, so that this side you can just left with this T over there. You get my point? So that you can just sum up punch everything on your calculator. So let's see what will be our T then. I'm gonna say fraction 2 into bracket ln of 20. Why am I pressing log? Ln of 20.1 minus 20 divide by this ln of 0.75. And then me on my calculator, did I press this correctly though? Oh, I forgot minus ln 20 there. Let me go and fix it. Minus ln 20. So it doesn't make sense. And then now on my calculator, what I get is 36.8345 something. So I get 36.83, just say 5. Ne? I'll just say 5. This is what I get. Minutes, obviously, because here we're talking about the minutes. 5, right? So let me round it to the whole nearest degree. It will be 37 minutes. So I mean, it will take 37 minutes. Like it will take 37 minutes for this thermometer to reach the room temp to be at equilibrium. Remember? I agree when you are in a room, you get into a room where it's hot and then you are cold, you're from outside. So what's going to happen is if the room has a constant temperature, what your body will do is your body will attain the temperature of the room until you get warm or until you get to reach the temperature of that room, until you no longer feel that you are cold or you are hot. You like your body and your temperature will attain the same, your body and your room will attain the same temperature throughout. You understand? So that's just how it works. I'm saying this because I'm looking at this question. So number 2, it says, is this realistic time? Motivate your answer. Is this realistic? By the way, yeah, because if you have a look at this, to motivate your answer, you're going to have to draw a graph. So the question is, how am I going to draw a graph? So now, when you draw your graph, on this side, we're answering number 2. On this side of the graph, on this side of the graph, okay, here we have the y-axis, right? And then here we have the x-axis. But you have to understand, on the y-axis, what do we have? We have the temperature, okay? In degrees Celsius. We have the temperature of the thermometer. Ne? And then this side, most definitely, we're going to have time in minutes. Let me just write in minutes, the time in minutes. Then here we have the temperature in degrees Celsius. Now, let us present, because we want to understand, is this a realistic time of a thermometer to reach the temperature of the room temperature? Initially, our time, it was 0. And then when the time was 0, our temperature was 40 degrees Celsius, right? So I'll assume that my 40 degrees is maybe somewhere else over there. And then after 2 minutes, we saw that the temperature was 35 degrees Celsius. So I will assume my 2 minutes is over here, and then I will assume my 35, maybe it's absolutely somewhere over there, so I can see how my graph is moving like this. And then when our temperature was 20.1 degrees, that what we have just calculated over here. Obviously, 7 is going to be far from there. I mean, 37 is going to be here. So for the fact that this is far from here, if I were to draw this graph over here, this will give me an exponential graph. Okay, it's an exponential decay, which for sure will approach an asymptote. In this case, it will be this line over here. Because remember, the temperature can never go further than this, by the way. So now what's happening over here is we can see that this is the realistic time. So we just motivated our answer drawing the graph over there, whereby we have a decrease, exponential decrease of our temperature along with time. So yeah, our session will end here, but I will be taking questions and whatsoever if we do have them. Do we all now understand? Let me stop the recording. Let me do this. So we are now all happy, guys. We understand. Okay, so
yeah, I'm good.
oh, you are good. Okay. What did you say? So come again?
No, I was saying I'm good.
You said say I'm good.
Yeah.
Okay. All right. All right. If you guys are good, then I'm happy. So I don't know. Is anything maybe that you guys want me to help you with, or you will comment in the group?
Or what we did now, or like everything in general.
I don't know. It could be this. Any. I don't know because so far, from the request, obviously, I got a request that you guys are fine with this thing. Wait, I want to stop the recording. You guys said you are fine with that again, kind um I'm bargaining the techniques. You guys are fine with techniques, obvious. The homogeneous, but be no